This lecture talks about differential equations. We're going to get started on this. We're going to talk about the theory first, and so we can, as mathematicians, justify our existence to the physicists and the engineers. We began with the description of the problem. It's an initial value problem, and it's stated here in its simplest, most basic form. That we have a derivative of a function x is equal to a function of two variables t and x. So the x prime of t is f of tx. And we have that x of t sub 0. So t sub 0 is a particular fixed number. X of t of 0 is equal to x of 0, which is another particular fixed number. And so let's have an example. Okay, here we have that x prime is equal to x times tan of t plus 3, and this should be an x prime of t, and this should be an x of t, but we suppress the arguments to make the writing easier. This is something that you do more and more of as the mathematics becomes higher level. So the initial value x of negative 3 is equal to 1. So this will pick off a particular solution. So let's go through and solve this. We've picked one we can actually solve here. Most of them we will have to do by numerical means. So x prime over x is equal to tan. So if I do the derivative, I integrate both sides. And when I do that, I'm integrating tan of t plus 3. I do a substitution, and it works out to a log. It somehow seems like they always work out to a log. And so the log of x is equal to negative log u. Then we do in resubstitution here, and the algebra works out to x of t is equal to the secant of t plus 3 is our final solution. Okay. Another example. Okay. Here we have x prime is equal to 1 plus x squared, and that x of 0 is equal to 0. And so what I've done over here, we've graphed this. The idea, we put a vector out, and so we put the slope of the tangent line over here in the xt plane. And so the idea is that you can get a feel of what the solution is going to look like if you just kind of follow the arrows from head to tail. And so this solution should kind of go up this way. I don't know if you can see my cursor or not, but it should follow up in that direction. And so we're led to the question is, okay, we're going to wind up integrating or excuse me, solving most of these numerically anyway. But the question is, okay, do they always have a solution? Okay, can you solve it? You can write down some stuff and maybe it's nonsense. Okay, can it be solved? And if it can be solved, then doing a numerical solution makes sense. So the first existence theorem for the initial value problem, and I think I misspelled existence, I never know. If f is continuous in a rectangle R that is centered at t naught x naught, say its R is equal to this expression here, then the initial value problem has a solution x of t for values of t that's less than the minimum of alpha. Again, this is our value of alpha. And beta divided by m, or beta being the limit on the size of our x, alpha was the limit on the size of our t, where m is the maximum value of f of tx on that rectangle. Okay. So we have a question here. X prime of t is equal to t plus sine of x of t squared, and x of 0 is equal to 3. Is there a solution for t between -1 and +1? Okay, so let's consider a rectangle in the xt plane that is centered at the point 0, 3, right? This is t and this is x. So I guess we should say it's the tx plane. And so our, t centers around 0. We're letting alpha be the upper bound. X is centered around 3. We're letting beta be the bound on the distance there. So f of t, x, hey, it's continuous. X plus t plus sine of x is and squared is as continuous as anything ever. Okay. Now, and it's positive, and so we can say that f of tx is bounded by, absolute value of t plus 1, okay, and then the t is bound, absolute value of t is bounded by alpha, so I can just plop in an alpha here, and sine, never gets any bigger than 1, never gets any smaller than -1. It's bounded by 1, and so forth. There we got it. Okay, so we want to choose, our alpha and beta so that the minimum value of alpha, beta over m, beta divided by m is at least 1. So alpha, we're just going to say, hey, it's 1. We don't want it any smaller than that. Okay. If that's the truth, okay, then m is smaller than this alpha plus 1 quantity squared. Alpha is equal to 1. I just roll that in, okay, and I've got the 1 there, so 1 plus 1 is 2, 2 squared is 4, okay, and so 1 over m, okay, is greater than or equal to 1 over 4. So if we insist that beta over m is greater than 1, we will have to have that beta is greater than or equal to 4. Okay, and so yeah, it can be solved, and for alpha equal 1 and beta equal 4. Okay, now here the thing is, okay, we actually want there to only be one solution. If there's more than one solution, it's going to mess up our numerical techniques. And so here's an example where having a unique solution fails. I mean, we've got this initial value problem, and there are two different solutions to it. Okay, is there a set of conditions that we can put on our different initial value problem so that it will have a unique solution? The answer is yes. Okay. The uniqueness theorem is if f and partial f partial x are continuous on a rectangle R as before, then the initial value problem has a unique solution on that rectangle. Well, for t absolute value of t minus t0 less than or equal to the minimum of alpha, beta divided by m. So, okay, so we have to have both f and partial f, partial x to be continuous on that rectangle. That fails in this case. We lose the continuity on the derivative because the derivative is unbounded. Okay. Now, this leads us to a second existence theorem, which is maybe easier to test. Okay. If f is continuous on a strip for t between a and b, and x going from negative infinity to positive infinity, and f satisfies what's called a Lipschitz condition. The absolute value of f of t x1 minus the absolute value of t x2 is less than or equal to L times L times the absolute value of x1 minus x2, then the initial value problem has a unique solution. So this is both existence and uniqueness.